Right, here we go. So we left off yesterday. We were looking at different types of forms we could have when we attempt direct substitution and we get an indeterminate form for an answer, which always means more work. But how do we do the more work? How do we approach this? What's our strategy? So yesterday we looked at rational functions, polynomial divided by polynomial, and that's always going to be the cancellation technique where we factor polynomials on the top and bottom and cancel the factors that are causing the 0 over 0 nature, right? Okay, we also looked at if we started off with complex fractions, right? If we started off with a bunch of fractions in the numerator, fractions in the denominator, and we had a couple options, we could either just kind of go old school and just simplify the top into one big fraction, bottom into one big fraction, and flip and multiply. Or my shortcut, great little trick, would be to clear all the fractions by distributing through the factors in every denominator, right? Every unique factor that shows up in the denominator, multiply that through. And we looked at an example like that. You get more practice in the homework. The third case that we had just started and didn't get through was what happens if you've got a limit that is indeterminate. So when I try to directly evaluate, I get 0 over 0, but it involves radicals. Okay, the trick is we want to remove the radical from the expression that's going to 0 by multiplying the top and the bottom of the fraction by the conjugate of whatever part is giving us issues. Like in this case, when we try to evaluate this directly, we get 0 over 0. So we've got this expression in the top, which is a radical minus 1, square root of x plus 1 minus 1, that's going to 0. So we're going to multiply the top and the bottom by the conjugate of that expression. Well, what do we mean by conjugate? We've got these two terms. We've got a radical and a non-radical. They could both be radicals, though. It might turn out that they're both radicals. We're going to multiply by the same binomial, only now instead of the operation being subtraction, it's going to be addition, right? So multiply by the square root of x plus 1 divided by itself. Okay, and magically this is going to work. Look what happens when we do this. Okay, on the top, what are we going to get? If I multiply conjugates together, let's remind ourselves about that real quick. When we multiply conjugates, a plus b times a minus b, what is the pattern we always get? Minus b squared. Okay, good. We always get difference of squares, a squared minus b squared. So if we apply that here, a is the square root and b is 1, right? So we should get what then? What is a squared in this case? X plus 1, right? Because the square root of x plus 1 squared gives us x plus 1 minus, what is b squared? 1. Good. Okay, now on the bottom, we are admittedly going to get kind of a mess, right? We're going to get x times that entire quantity. So we get x times the quantity square root of x plus 1 plus 1. And you might be thinking, well, big deal. I mean, now we just got another radical expression that's going to cause problem, but it's not. Because if I evaluate directly, is that factor going to go to 0? It's not, right? We're going to get square root of 1 plus 1, which gives us 2, instead of square root of 1 minus 1, which gave us 0, right? And so this works out fine then. If we simplify this expression one more step, what do we get on the top? X. There you go. We get x. On the bottom, we get x times the quantity square root of x plus 1 plus 1. And what happens algebraically? What cancels? The x's. Didn't we know that had to happen though? Because what's the factor that's going to go to 0 when x approaches 0? X, right? Right? Isn't that the factor that when x goes to 0, the factor that would go to 0 would just be x, right? We can always remember back to algebra 2, if remember this stuff, if we'll call it a different number, if c is a factor, or is it 0? Sorry. Oops. There we go. If c is a 0, then x minus c is a factor. Remember our factor theorem when we were dealing with polynomial stuff back in Honors Algebra 2? Well, that's kind of what we're doing here, right? As x approaches 0, well, what's going to be the factor that goes with that? X minus 0, right? Just like if x were approaching 2, the factor that we would have to cancel would be x minus 2, right? Does that make sense? Okay. So we already knew somewhere in our future, at the very beginning of this problem, we were going to be canceling x's on the top and bottom, and here's where we do it, right there. Okay, we just had to algebraically massage that argument until we got there. Okay, now we get a limit that is no longer indeterminate because we canceled the factors that were causing the indeterminacy, that were giving us the 0 on the top and the bottom. So we get, oops, we get the limit of what's left on top. 1. And on the bottom, we've got square root of x plus 1 plus 1. As x goes to 0, that term disappears, and I just get 1 over square root of 1 plus 1, 1/2, right? Done. Okay, so we got 3 techniques. Rational function that's indeterminate, factor top and bottom, cancel the factors. Complex fraction, clear the fractions to make a rational function, and then cancel the like factors. Indeterminacy involving radical expressions, you're going to use a rationalizing technique, and you're going to rationalize by multiplying top and bottom by the conjugate of the radical expression that's going to 0. Okay. All right, so here's another example. Like if we were taking this, is that the one we just did? Oh, it is. That's very similar to the one we just did. Okay. Anyway, there's steps. I mean, you can look at this, and I'll leave this in here for your notes. Okay, what about that guy? What are we going to do? Okay, are you sure you're making an assumption though? Yeah, always try to evaluate directly, right? And if we evaluate this one directly, what do we get? Negative 12. Okay, well, it's not 0 on the top, right? So this is not going to be indeterminate. And on the bottom, we get square root of 16, right? 24 minus 8 is square root of 16, which gives us negative 12 over 4, which is negative 3. Done. You see my point. Don't jump to conclusions. Always try to evaluate directly, because sometimes you don't have to do anything complicated at all, right? This was a type 1. We evaluated directly and we got a numerical answer. We're done. Okay. How about that one? What do we try first? Evaluate directly. What do we get? 0 over 0, don't we? In this case, we do get an indeterminate form, 0 over 0. So it's more work. What is our more work going to look like? Okay, good. We got to multiply top and bottom by the conjugate of the bottom because the bottom is the one that has the square root in it, right? Okay, so we'll do this. Let's put these guys in parentheses and we'll multiply inside our limit. We're going to multiply by square root of 4x plus 5 plus 3. What do we get on the bottom? We're multiplying conjugates. So a squared or a minus b times a plus b is a squared minus b squared. What's a squared? 4x plus 5 minus 9. Okay, give me thumbs on that. Everybody see how we got that on the bottom? Okay. This is, and again, this is just for your notes, this is like a squared minus b squared, right? Where this part is a, that part is b, right? We're just following that pattern, okay? On the top, we just get what we get, right? On the top, we get the factors x minus 1 times the quantity square root of 4x plus 5 plus 3, and the limit as x goes to 1. Okay, so what's next? Looks like a mess. What do we do here? What do you think? We have to, right? So what is the factor? If x is approaching 1, what do we know the factor that's going to cancel is going to have to be? Yeah, we're going to have to cancel an x minus 1 on the top and bottom, right? That's telling us we're going to cancel x minus 1 over x minus 1. We already know that's going to happen. Well, there's my x minus 1 on top. What about the bottom? I don't see an x minus 1. What do we have to do? Do I need those parentheses? I just put them there because that's a squared, but there's nothing being distributed. It's not to a power, so we don't need them. So what do I get on the bottom if I simplify? 4x minus 4. Okay. So limit of that big mess on the top divided by 4x minus 4. Okay, what can I do on the bottom now? I need an x minus 1. Factor out of 4. There you go. Okay, that's better. What happens? Yeah, exactly what we predicted, right? This happens. The x minus 1's cancel. We remove the indeterminacy, and now we can just evaluate our limit. Okay, when I evaluate directly now, what do I get? 6/4. Everybody agree? Okay. Three halves. That's it. Okay, good. We got it. All right, so what about something like that? Okay, does that look pretty weird? Why would I give you a problem? Why? That's just why, Mr. Ryan. Okay, because this is a glimpse of your future. This is a really important limit. These are the whole reason we're doing these limits, or 99% of the reason we're doing these limits, is to be able to evaluate limits that look like this. This is going to become what you're going to soon recognize to be a derivative function. Okay, but we're not there yet. You don't know how that's going to be a derivative. We'll have to talk about that and build up that concept. But you're going to be doing those kinds of limits. So let's practice them before we get into the conceptual part of this. Before we get into the calculus, how can we do a limit like that? What do you think? If I try to evaluate this directly, what do I get on top? As h goes to 0, what does x plus h become? Yeah, it just becomes x, which we're going to square, right? So I end up with 8x squared minus 8x squared, which is 0 over 0, because h is going to 0, okay? So this is indeterminate. Now, how many people are having a little trouble with the fact that there are x's and h's in that? Is that causing some consternation? I bet it is. Okay, well, which one of those is the variable of the limit? Okay, now think about this in terms of what is the limit acting on? As far as the limit is concerned, the variable is what? H, because that's the value that's approaching something. From the limit's perspective, x is not a variable, right? It's not changing in the limit, right? We don't know what x is not approaching anything. X is just x. So what do you think we do? What do we do? No, we might get x's in our answer. That's okay, because the x is not a variable as far as the limit's concerned. We want to try to set this up so that what's going to cancel here? H. We need to be able to cancel a factor h in the top and bottom, and then we'll be able to take our limit as h goes to 0. We can evaluate directly, and the h's are going to be replaced by zeros. We never said anything about the x's, though, did we? Right? The x's are not being acted on at all in this limit problem, right? Okay, so moral of the story. Something must cancel. What's going to cancel? You already told me. The h must cancel. Why must the h cancel? Because of that, right? You guys are already, you could have anticipated that, okay? All right, so then we just have to do algebra to make this happen. This is actually not a hard problem. It's not like we've got some kind of complex fractions or radicals going on. This is just, if I expand this, this is just going to be a polynomial divided by a polynomial, right? So what's my first step? What do I need to do here? When we do algebra, like what? Expand that out, right? I have to expand out x plus h quantity squared. Okay, so if I do that, that's going to give me limit of, let's do this. Let's kind of color code this a little bit. So we're going to take all this stuff and replace that with green. So I get the limit of 8 times what? What is x plus h quantity squared? You guys know that pattern, right? X squared plus 2hx. I'll just call it x. Not that it matters. Xh doesn't make any difference. Plus h squared. Good. Okay, that's our binomial expansion, right? Minus 8x squared over h as h approaches 0. Okay, what's next? Not factor it out. What do you mean? Distribute the 8, right? How come? Because we want to be able, we want to completely expand this so we can combine like terms on the top. Okay. What do you think is going to happen? Okay, the 8x squareds are going to cancel out. And well, we'll see what happens here. So the 8x squareds cancel. So I'm going to get limit of 8x squared plus 16xh plus 8 at x squared, h squared, sorry, h squared minus 8x squared over h as h goes to 0. And yes, look what happens here. The x squareds cancel horizontally. They add to 0, right? So they're gone. Now what? You guys told me that the h's have to cancel. I have to be able to cancel factors of h. I don't see a factor of h on the top yet. But I could factor out an h, couldn't I? So if I factor out an h, what's left behind on the top? 16x plus h over h as h goes to 0. And there's that cancellation that you guys predicted, right? There it is. The h's cancel. So now the indeterminacy is gone. I no longer get 0 over 0 when I directly evaluate. And so what's going to happen when I let h go to 0? I just get 16x, don't I? Yeah. And here's our h going to 0. And so we get 16x. So we got x's in our answer. That probably seems weird to you now, but soon you would expect that. When we're doing a derivative, when we start talking about this in terms of derivatives, you would expect to get an x in your answer. Not now, that's future, but that's what we get, okay? I know that looks mysterious, but you'll be doing a lot of that. Okay, so I'm gonna give you some special limits here. And I'm not gonna derive this. I always really enjoy deriving this because it's really a cool little proof you can do. It's a geometric proof, but I'm not going to take the time. If we're trying to push through and do this AP test, we got to make tracks. So maybe after the AP test, we'll come back and look at this. Okay, so these limits that we could test, these are always true. Now, this looks like an indeterminate form, right? The limit of sine x over x as x approaches 0. If I evaluate directly, I get 0 over 0, indeterminate. I'm just going to tell you, though, that the answer to that one is 1. And we could verify it by looking at a graph or looking at a table or something. And then the other one is the limit of the fraction 1 minus cosine x all divided by x as x approaches 0 is also equal to 0. Those two special trig limits, we can just use those when we encounter indeterminate forms of trig limits, okay? So like, what do I mean by that? Okay, so what if we start with it? Let's look at this example. The limit of tangent x over x as x approaches 0. We got to evaluate that. If I try to directly evaluate, what's the tangent of 0? Okay, if you're not sure, the way you always want to do tangent is think of it in terms of sine over cosine, right? So tangent of 0 is the same as sine 0 over cosine 0. What's sine 0? 1. What's cosine 0? Other way around. Sine 0 is, do you guys, we probably need to do, is 0. Yeah. Okay, are you guys like super pros with the unit circle? Because the unit circle, is, you can do everything on the unit circle. I promise you. Here, let's do it real quick. We'll come back to this. I used to, you know that pretty well. Okay, so on the unit circle, if you can think in terms of unit circle, all this stuff gets really, really easy. So our unit circle, yeah, and it's super easy. So if we've got a point on the unit circle, I don't really care. I'm not going to focus on the points, the known points on the unit circle for now. You guys, although I'll show you, you guys know the finger trick for that? Oh my gosh, I got to show this to you. This is so good. Okay, so we'll do two things. First of all, let's look at this in terms of an angle theta. So let's not look at a specific angle, but if this is an angle theta and this is a unit circle, that's 1, right? That's what unit means, is 1. The radius is 1. Okay, in terms of trig functions, what are the coordinates of any point on the unit circle? What does the x component of any point on the unit circle correspond to? Corresponds to cosine. The x component. You guys, do you remember this stuff? And the y component is sine theta. It's easy to keep those straight because they're alphabetical. X before y, c before s, right? So cosine goes with x, sine goes with y every time. If you're looking at individual points on the unit circle, oh, this is such a good little trick. And you won't need it for long because you'll just remember these points pretty soon. You use them so often. But what are our points in our known points in quadrant 1? Because we can just reflect those to get the other ones. That's easy, right? If we know quadrant 1, we know them all. What are the coordinates of that point? What are they again? Now, 1, 0, right? There you go, 1, 0. 1, 0. And this one is 0, 1. We just need the in-between ones, right? Okay, so we've got 3 of them. We've got one there, we've got one there, and we've got one there. How about this guy right here? What is it? I want to know what are the coordinates. You're right, it is pi over 6. Okay, that's true. So this is pi over 6 radians. Okay. Can I show you guys a trick? Okay. Here's a trick. Okay, put your hand up here. This is the x-axis, that's the y-axis. Okay? Okay, so now when you want to know the coordinates of this point right here, that's the point that lies on the x-axis. So we fold in that finger. Okay? To the left of the fold, the square root of that number. How do I do that? Yeah. so I'm folding that one in, right? Yeah. So then the numerator, the denominator is always going to be 2. The numerator is going to be the square root of the number of fingers to the left of the fold and the right of the fold. Okay? So to the left of the folded finger, it always goes xy, right? So the x coordinate is going to be the square root of 4 over 2. 2 over 2, which is 1. The y coordinate is the square root of 0, which is 0 over 2, which is 0. So I get the coordinates 1, 0. Okay, let's go up to this point. That's that fold, right? Okay, so the x coordinate is the square root of 3 over 2. The y coordinate is the square root of 1, which is 1 over 2. Aha! So look at that. We get square. I'm so excited I can't even write this. It's just. Okay, square root of 3 over 2, 1/2. Now we go up to this guy, so I'm folding in that finger. X coordinate is square root of 2 over 2. Y coordinate is square root of 2 over 2. How about that? Right? Go to this guy. Now I'm folding in that finger, so the x coordinate is square root of 1, which is 1 over 2. Y coordinate is square root of 3 over 2. And then that one works too, doesn't it? I fold the thumb down. Square root of 0 is 0, so I get 0 over 2, or 0 for my x coordinate. Square root of 4 is 2. 2 over 2 is 1. 1 for my y coordinate. Ta-da. Okay, how about that? Make sense? Okay, here's another way to keep that straight. The more ways you have to think about this, the easier it is to remember. If you think about if you think about all the different numbers that show up uh, in the coordinates in quadrant 1, let's put them in order. The smallest is 0. The next smallest is 1/2. The next smallest is square root of 2 over 2, because square root of 2 is bigger than 1, right? The next biggest is square root of 3 over 2, because square root of 3 is bigger than square root of 2. And then the biggest is 1. Okay, well, what do you notice? You always get, there's going to be symmetry. You get the middle one with the middle one. You get the slightly small one with the slightly big one. You get the very small one with the very big one every time, right? It maintains that symmetry, okay? And so if you're looking at this in terms of these points, how would you describe that point? Well, that's very big X, very small Y, right? This one is slightly big X, slightly small Y. This one is medium X, medium Y, and so on and so forth. So you always know which ones go with which if you just put those in order, okay? So you can always keep that stuff straight. Make sense? Okay. All right, so we'll get back. We'll break this into pieces. Thus ends part 1 of unit circle review. Okay, so now we're back to this problem. So if we try to evaluate this directly, then we've got sine of 0 over cosine 0. Well, sine of 0 is going to be the y coordinate of 0, which is 0, divided by the x coordinate of the point over here at 0, which is 1. 0 over 1 is 0 over 0. 0 over 0. It's indeterminate, okay? So we've got to do some math on this to evaluate this limit. The way we do math on trig functions is we've got to rewrite this using trig identities and trig definitions to have one of these two, and it's 99% of the time, it's that one, that trig limit to pop out, okay? So what's our strategy here? Whenever you're doing trig algebra with a composite trig function, right? We always want to write the composite trig functions in terms of the base trig functions, sine and cosine. Always write tangent, cotangent, secant, cosecant in terms of sines and cosines. That always makes things easier, right? So then we'll rewrite this as the limit of sine x over cosine x divided by x, which is the same thing as x over 1, right? As x approaches 0. Now what have I got? Fraction divided by fraction. So what do you always do when you have a quotient of fractions? Say it again. Okay, and how do you do that? Well, okay, I mean, okay. Yeah, I mean, you could do that. In this case, that's actually more complicated. We just always want to flip and multiply by the bottom, right? Fraction divided by fraction, you multiply by the reciprocal of the denominator to make it a product instead of a quotient, right? So we would write this as the limit of sine x over cosine x times 1 over x, right? Agreed? Okay, so on the bottom then, I'm going to write that one more time. The bottom, we could combine that to look like the limit of sine x over x cosine x as x approaches 0. Okay, why did I do that? Yeah, look what I could do. I could split this up. I could split this up into a product of, so I've got the limit of, exactly, of sine x over x times 1 over cosine x as x approaches 0, okay? Okay, this takes us back to some properties of limits. So let's scoot down just a little bit here. Remember, we have this property of limits that says if the limit of f of x as x approaches a equals L, and the limit of g of x as x approaches a is m, then you guys tell me, what's the limit of f of x times g of x as x approaches a? L times m. Yeah. So the moral of the story there is, the intermediate step is, we can always break this into a product of separate limits. So listen carefully. This is going to sound a little confusing. The limit of a product is equal to the product of the limits. Okay, so what's that mean? The limit of a product, right? So the limit of f of x times g of x, that's a product, they're being multiplied, is equal to the product of the limits. Okay, right? So I need to include, I need to include that as x approaches a, technically, right? And so what's that equal? Well, this limit is equal to L, that limit is equal to M. Okay, so in this case up here, we can apply that property. If I have the limit of a product, I can split this into two separate limits, right? So this is equal to the limit of sine x over x as x approaches 0 times the limit of 1 over cosine x as x approaches 0. Okay, does that blue one look familiar? How about that? That's equal to 1, okay? Now, my son has been chastising me this year for not teaching that in terms of the small angle limit, but I'm not going to do that today. Don't tell him. I'll come back and show you the small angle approximation later, and you'll see how that works. It's what's beautiful about calculus is everything just kind of comes together here, and it always is so consistent. Like you can look at this stuff in a bunch of different ways, and it always comes together. So he's doing calculus in college, and we were talking about what we're doing in class, and just to defend that a little bit, he said, well, God, why do you teach it that way? Why don't you just show them the small angle approximation, and then they can just figure it out from there? And that's a good point, but I just sense that that's not a good thing right now. I'm throwing too much new stuff at you. So we'll come back to that. So this limit, this is a known limit. That one always is equal to 1. How about this guy? If I take this limit and I evaluate directly, what's the cosine of 0? 1. So I get 1 over 1. My answer is 1. Look at that. How cool is that? That's pretty slick, right? Okay. So you can always lean. And again, this is the one you need to know. This one right here, you almost never use. And not today, but when we do some more trig review, let's just show how we can derive this one from this one next time. It's super easy to do. If you know this one, you know them all. You can always come up with that one in like 4 steps. Are we out of here in like a minute? Oh my gosh, this goes so fast. I feel like we've only been doing this for 5 minutes. I could go another 3 hours on this. Say it again. I can. Right there. Yep. I bet you could too. I bet you guys are just dying to do a little more of this probably. But the small angle. So all the small angle approximation is this. The small angle approximation just says this. As approaches 0, sine x approaches 0. That's all it is. Okay, that's the small angle formula. And so you could, from this, you could come up with a construction where you can prove all this stuff just using the small, but we'll deal with that later. Yeah. Okay. I'm going to get rid of that last part. I don't want that on my notes for now. Actually, so I said that wrong. I'll tell them tomorrow. It says as x approaches 0, sine x approaches x. Yeah, yeah. Oh, so it's I said that wrong. It's as x approaches 0, sine x approaches x. So in the limit, that becomes x over x. See what I'm saying? Yeah.